A warm welcome to all the students. We started with the discussion on chemical kinetics in our last session, Chemical Kinetics Part 1, in which we discussed the basic terminology related to chemical kinetics and also zero-order reaction, first-order reaction, and second-order reaction. Let's carry our discussion further on the same topics and some new ones also in this session, which we are going to call Chemical Kinetics Part 2. We have already discussed what are zero-order reactions, first-order reactions, and second-order reactions. Now let's have a look at pseudo first-order reactions. Pseudo first-order reactions, as the name itself indicates, are those reactions which are not of first order and are actually of higher order but behave like first-order reactions. Let's take an example, the hydrolysis of ethyl acetate. As you can see in the reaction that there are two reactants, acetate and water, which react to form acid and alcohol. But the concentration of water is so large in this reaction that it practically remains constant throughout the reaction. Therefore, the reaction and its rate will depend only on the concentration of one reactant, that is ethyl acetate. So, if we look at the order of the reaction is 0 with respect to water, as its concentration remains practically constant, and 1 with respect to ethyl acetate. And so the overall order of reaction will also be 1 plus 0, that is 1. Therefore, it's a pseudo first order reaction. As we can see in its rate expression, the rate depends only on the concentration of ethyl acetate and not of water. Let's have a look at some of the examples of pseudo first order reactions. The first reaction is the reaction between acetic anhydride and ethyl alcohol to form ethyl acetate and water. Ethyl alcohol, as mentioned, is present in large quantities and therefore the rate of the reaction depends only on the concentration of acetic anhydride. The second example is the reaction of carbonyl sulfide with water, which is present in large quantity, to form carbon dioxide and hydrogen sulfide. Now again, since water is present in excess, the rate of the reaction will depend only on the concentration of carbonyl sulfide, and it's a pseudo first order reaction. The next example is the hydrolysis of sucrose to form glucose and fructose. Water is present in large quantity, therefore the rate of reaction will depend only on the concentration of sucrose, making it a pseudo first order reaction. Our next topic is the Arrhenius equation, named after the Greek scientist Arrhenius. It is a mathematical equation which represents the variation of rate constant of a reaction with the temperature. It is given as K is equal to A into small e raised to minus EA divided by RT, where small k is the rate constant, A again is a constant named as frequency factor, EA is the energy of activation, R is the gas constant, and capital T is the temperature. Now if we take natural log on both the sides, we can write it as natural log K is equal to natural log A minus EA divided by RT, or taking the base as 10, log K is equal to log A minus EA upon 2.303 RT. We use an assumption that if the temperature does not vary much, A, that is the frequency factor, and EA, that is the activation energy, remains constant in that case. We are going to use this assumption when we find out the correlation between the rate constants at two different temperatures. Also, the unit of frequency factor A depends on the order of the reaction and is the same as that of K. Now we got two equations. The first one was log K is equal to log A minus EA upon 2.303 RT. Now if we compare it with a straight line equation, that is y is equal to mx plus c, and plot a graph between log k on y-axis and 1 by t on x-axis, we'll get a straight line whose slope will be equal to minus EA upon 2.303 RT, and the intercept on the y-axis will be equal to log A. The other form of this equation that we obtained was natural log K is equal to natural log A minus EA upon RT. Again, if we plot a graph between natural log of K on the y-axis and 1 by T on x-axis, we'll again obtain a straight line graph with slope equal to minus EA upon R and intercept on y-axis equal to natural log of A. This is the graph that we were talking about. Natural log K is plotted on the y-axis and 1 by T on the x-axis. We obtain a straight line for the equation whose slope is equal to minus EA upon R and the intercept on y-axis, that is this portion, is equal to natural log of A. At two different temperatures, say T1 and T2, if the rate constants are K1 and K2 respectively, then we can write the Arrhenius equation for each temperature as log K1 is equal to log A minus EA divided by 2.303 RT1 and log K2 is equal to log A minus EA divided by 2.303 RT2. We must keep in mind that since the temperatures do not vary very largely from each other, we are considering A, that is the frequency factor, and EA, that is the activation energy, as constant. That is, it is same for both the equations at both the temperatures T1 as well as T2. Now, if we subtract this equation from the other one, we will get log K2 upon K1 is equal to EA divided by 2.303 R into T2 minus T1 divided by T1 T2. Let's solve this question. The inversion of cane sugar follows second order kinetics. The reaction can be depicted by the following equation. C12H22O11, that is sucrose or cane sugar, it reacts with water. It undergoes hydrolysis to form glucose and fructose. The chemical formula for both of which is C6H12O6. Now at 300 degree Kelvin, the rate constant, that is small k, is equal to 2.12 into 10 raised to minus 4 liters per mole per second. And at 310 Kelvin, the rate constant is equal to 8.46 into 10 raised to minus 4 liter per mole per second. We have to calculate the value of activation energy. Now we just discussed the equation which correlates the rate constants at two different temperatures. Log K2 upon K1 is equal to EA upon 2.303 R into T2 minus T1 upon T1 T2. Now at 300 Kelvin, that is temperature T1, the rate constant, that is K1, is given to us, and similarly at T2, that is 310 Kelvin, the value of rate constant, that is K2, is also given to us. R is the gas constant whose value we know is equal to 8.314 joules per Kelvin. And we have to calculate EA, that is the activation energy. So if we substitute these values in this equation, we get log 8.46 into 10 raised to minus 4, this is K2, divided by K1, which is 2.12 into 10 raised to minus 4, is equal to EA upon 2.303 into 8.31 into T2, that is 310 minus T1, that is 300, divided by T1 into T2. Now if we solve this equation, then we find that EA is equal to 107,000 joules per mole. This is the activation energy and our final answer. In the second question, we have to calculate the value of frequency factor for the same reaction with the same data. Now we have calculated activation energy in the last part. So if we write the equation log K is equal to log A minus EA upon 2.303 RT. Now, if we consider this equation for the first set of conditions, then we can write log K1 is equal to log A minus EA upon 2.303 RT1. Now, if we substitute the values in this equation, then we can write log K1, that is the rate constant for temperature 300 Kelvin, that is T1 is 2.12 into 10 raised to minus 4, which was given to us, is equal to log A. We have to calculate A, that is the frequency factor, minus activation energy. We have just calculated, it is 107,000 joules per mole, divided by 2.303. We know the value of R, that is universal gas constant, it's 8.314 into T1, that is 300 Kelvin. So if we solve this equation and bring this part to this side, then we get log A is equal to 14.877, or A is equal to 9.71 into 10 raised to 15 liter per mole per second. Now, if you remember, we discussed that the unit of A is same as that of K. This is a second order reaction, and the unit of rate constant for second order reaction is liter mole per second. So the unit of A will also be liter per mole per second. The third part of the question says that calculate the value of the specific rate constant at 320 K. So we can write log K is equal to log A minus EA upon RT. Now we have to calculate this K. We have calculated the value of A, that is the frequency factor, and EA, that is the activation energy. And since we made the assumption that their value does not change if the temperature does not vary much, we will assume that A and EA remain the same for all the three temperatures, that is 300K, 310K, and 320K. So on substituting the values, log A, we just calculated the value of A, which came out to be 9.71 into 10 raised to 14 minus EA. We have also calculated the activation energy, that is 107,000 divided by, sorry, it's 2.303 divided by 2.303 into R. We know the value of R, that is gas constant, it's 8.314 into T. T is given to us, that is 320. On making these calculations, we find that log K is equal to minus 2.507, or K is equal to 3.11 into 10 raised to minus 3 liter per mole per second. So this is the value of rate constant and our final answer as well.